guys, welcome to part 2 of continuous charge distributions, in which we are going to look at example 1 from your notes packet. So it says that we've got this semicircular section of wire. Okay, fine. In other problems, it might not be a semicircle. They'll be like, yeah, you know, it's 2 theta, whatever that is. Or maybe it's a third of a circle, or even 2/3 of a circle, or something else. Okay, so just it's some portion of a circle, and they want to know what's the field at the center and what's the electric potential at the center. And those are usually the 2 things that they're going to ask for whatever portion of a circle it may happen to be. In some questions, they will give the charge density, lambda, and in other problems, they will tell you the total charge Q. So at the end of this video, or near the end of the video, we will practice turning it from lambda to Q, because they could give it to you either way, and so you have to be able to essentially change formats from one to the other. Okay, now, in the previous video, we talked about the steps of solving one of these problems. And you know, there were 5 steps, and in isolation from an actual example, they may not have made like a ton of sense. So my goal here is to make them make more sense by putting them in the context of a real problem. Okay, so here goes. Part A, they want you to find the electric field at that point. All right, now way over here is my electric field formula. I'll go ahead and write that down. All right, and now the second bit is choose an origin on the object. We said last time that's usually going to be in the middle. Sometimes it's the point on the object that is closest to the point where you want to find the field. All points on this are the same distance away from it, so we'll pick the exact middle. All right, fine. Next, define variables using the diagram and a charge element. Remember we said don't put the random little bit of charge here at the origin and don't put it at the very end. The goal is for it to be somewhere like actually kind of random, all right? So we'll put it there. There's my charge element, dq. Let's see, and so this distance, since it's a circle, is the radius of the circle. Oh, and so is that distance. In fact, all bits of the circle are the same distance r away from that point. Okay, next. Put dq in terms of all this junk right here. All right, now from the last video, we learned that dq is always going to be lambda r d theta. Let me pause for a moment here and see what else we can substitute in here. We'll talk about r hat momentarily. We also need to talk about exactly what theta is. But the r here, r is the distance that a particular charge element is away from the point where you want to find the field. If you had some other shape of charge distribution, r would be a function, okay? If it were a straight line, r would be, well, a different value for a charge element here versus at the very end of the rod. You'd have a function down there, and you'd have to use like Pythagorean theorem to work out what all those distances are. In this case, every little bit of charge on this wire is the same distance away. So little r squared is actually just the radius of the circle, because all points on a circle are the same distance away from the focus of the circle. There we go. That's all we got to do for little r. All right, now let's talk about what theta and therefore r hat are going to be. Theta is going to be this thing right there, okay? It's the angle between the origin and the position where you have drawn your charge element. Now, different charge elements are at different thetas, and so that's where the integration comes in, right? The idea of doing an infinite summation of all of those individual charge elements. It's also going to matter for doing r hat, though. So let me, at this point, pause for a moment and say, this right here is the electric field, but we, based on the setup of the problem, are going to now break up this thing into two integrals. That sounds very scary. Two integrals. I thought I only signed up for one integral. What the? Okay, no, just calm down. One of the integrals is going to equal 0. Yeah, one of them is just going to flat out go away. Now, the reason there are two integrals is because of r hat. Reminder from ancient days, r hat is equal to cosine theta I plus sine theta j, as long as you have defined an angle from the horizontal, which we have. So that's great. The angle's defined from the horizontal. That means that this is correct. So it's going to break up into one integral for all of the x components and another integral for all of the y components. All right, now we only actually need to do one of these integrals. We only need to do, put your thinking cap on here, pause the video if you have to, think about which one of those two integrals is going to be 0. All right, and now that you have resumed, so if I were to draw all of the electric field lines from all of these individual charge elements, it would get a little overwhelming, okay? But, you know, on balance, you could say, all right, let's draw a few of them, okay? On balance, looking at that, looks to me like the up and down bits are going to cancel out, right? For every one that goes up, there's another one going down. But they all basically go to the right. That's assuming, of course, that this is a positively charged curve, which I implied that it was at some point. Okay, so because the up and down bits are canceling out completely, that means that the electric field along the y-axis is going to be 0. Okay, now, in a moment we might discuss more exactly why that is, or you can prove it to yourself after you're done watching this. But let's go ahead and say for now, based on reason and things that I've drawn, the y components will just completely cancel out and we'll have 0. So that means that the only electric field that we actually have to evaluate using calculus is the x component. All right, which means now I write my integral as cosine theta I hat, if I like. The I hat won't really do anything. It'll just be in our answer. All right, now we can simplify that, and then I'll go ahead and worry about step 5. So simplifying things a little bit, you can see that one of the r's will cancel, and lambda and r are both constants. I can go ahead and pull them out of my integral. And what I will see I have is cosine theta d theta. So all you're really doing then is integrating cosine. And that's an integral that you probably ought to be familiar with. Even if you haven't done it in calculus class, we've done it in this class before. Okay, so last thing to do is determine the limits of integration. Since this is a semicircle, right, the whole thing is pi over 2, or sorry, that's not true. 2 pi radians is a complete circle. So a semicircle then would be pi radians. Our limits are not going to be 0 to pi. My origin is right here in the middle. Okay, it's important that you pick that origin, actually mostly so that the cosine and sine things end up being what we said they were. Okay, but there's our origin. It's pi radians the whole way from this end to that end, but with 0 in the middle, that means that it's going to be negative pi over 2 to pi over 2. Okay, and now we can integrate that. All right, the integral of cosine is sine. Okay, that's something that is provided to you on the AP, but probably just good to know it off the top of your head. So therefore we have k lambda r sine theta evaluated from negative pi over 2 to pi over 2 I hat. All right, sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. So when we do our whole plugging in the bounds thing, we're going to have k lambda over r 1 minus negative 1. Okay, so when all is said and done, simplifying that, the electric field at point P is going to be 2k lambda over r I hat. And we're done. That is the answer for part A. All right, now at this point, actually, you might have some idea how you're supposed to set up part B. So if you feel like you get it, go ahead and do it. That integral is actually going to be a lot easier, though, because it's not going to involve components, right? Potential is just a scalar quantity, so that means that you're not going to have to worry about cosine and sine. Those won't even be in there. There's no r hat in the equation. If I could get back to this idea before we go on to potential, try out this essentially same integral, but integrating sine from negative pi over 2 to pi over 2. And what you will find out for that one is you'll get a bunch of zeros. So you can try that one out on your own after the video is over. Okay, so I'm going to sort of suddenly populate most of the work for B, because a lot of it is just going to be repeating what we did in part A in terms of defining our variables. Okay, so here we go. So part B, finding the electric potential, we pick this formula. Just like last time, little r is the radius of the circle. It's a constant value. And dq is replaced with lambda r d theta. And our limits of integration are from negative pi over 2 to pi over 2. So simplifying this, we're just going to get k lambda, the r's cancel out, integral of just straight up d theta. All right, now if you don't remember how to integrate just d theta, it's theta. That's it. So when we plug in our bounds, we will get k lambda pi over 2 minus negative pi over 2, which will give us pi. So final answer, the electric potential is k lambda pi volts. All right, now the last thing that we'll do here is rewrite our answers in terms of Q. So I'll do one, and then you can pause the video and see if you can figure out the other one. Now remember, the idea here is sometimes the AP gives you the linear charge density of the curve, but other times they tell you that the total charge is Q. So you have to be flexible. This is the answer that you would probably initially get. But if they said, oh yeah, it's got a charge of Q equals 2 nanocoulombs. Oh, what do I do with that? Well, what you do with that is, remember, lambda is Q over L. The length that we have here is half of a circle. Okay, that's going to be r theta. Every time L equals r theta. So in this case, theta is pi. It's half of a circle. So therefore, lambda equals Q over pi r. Plug that in over here. And this is the result that we get for the electric field. All right, I'll pause again, and you can try out part B. Ta-da!